Hi, hi. This is in continuation to our previous video lecture. We were done with sodium chloride structure, and I've just shown you that in cesium chloride ionic structure, in the ionic structure of cesium chloride, we have these chloride ions at the corners of the cube. Right? Let's draw it here. Just rub this. So the chloride ions would be present at the 8 corners of the cube, right? And cesium ion is present at the center of the cube, right? If this is your cube, right? We have chloride ions at all 8 corners of the cube, right? And cesium ion, the Cs, at the center, right? Now just make sure you understand one thing, that the structure of cesium chloride is simple cubic cell, right? It's simple cubic unit cell, right? This is not body centered body centered unit cell. It is simple cubic unit cell, right? And not a body centered cubic, right? So the structure is simple cubic. The unit cell is simple cubic unit cell of cesium chloride and not body centered cubic, not BCC. Now you have one particle at the center, then why not BCC, right? If you remember, when we talk about unit cells, the particles that are arranged is similar, right? Here the similar particles are chloride ions, right? So these chloride ions are arranged in simple cubic. The arrangement of these chloride ions are simple cubic, right? And there's only one cesium atom, right? It's only one cation, which is cesium, which is present at the center, right? Since this particle at the center is not chloride ion, if this would have been chloride ion, then this structure would have been body centered cubic, right? But since the similar ions which are present are only at the corners of the cube, so this is simple cubic unit cell, right? So we say the structure of the unit cell of cesium chloride is simple cubic unit cell, right? Now we have one thing, what is the effect of temperature and pressure on the structure of these ionic solids, right? So effect of temperature and pressure on these ionic solids, right? We know that the structure of any ionic solid, right, is related to the coordination number, right? Now if you look at this cesium chloride, what is the coordination number of cesium? The coordination number of cesium is its nearest neighbors, right? That are surrounding this cation, which is cesium. So it is 8 chloride ions are surrounding this cesium ion. So cesium has coordination number of 8. Similarly, any chloride ions, if you look at any chloride ions, this would be surrounded by 8 other neighboring atoms or ions, sorry. So any chloride ion would be surrounded by 8 other ions, right? So it would be, for chloride ions, it would be surrounded by 8 other chloride ions, so coordination number would be 8. So 8 for cesium and 8 for chloride ion, right? And if you want to see how many particles are present in the unit cell of cesium chloride, right? So the coordination number of chloride as well as cesium is 8, right? So the contribution of chloride ion would be, as we have said in the previous video lecture, in case of chloride ions which occupied the 8 corners of the cube, only 1/8, right, belong to 1/8 of any chloride ion, right? Since we said that this chloride ion, right, would be shared by 8 other unit cells, so it at this corner, this chloride ion, 1/8 of this chloride ion would belong to this unit cell, and we have 8 corners. So number of unit cells would be, number of chloride ions in this unit cell would be 1 upon 8. 1 upon 8 into 8, it would be 1, right? And 1 is present at the center, right? 1 cesium ion at center. So number of particle is 1 chloride ion and 1 cesium at the center, right? And we were talking about the effect of temperature and pressure, right? So high pressure will favor high coordination number, and high temperature will favor low coordination number, right? So if we apply high pressure on cesium chloride, on sodium chloride, then its coordination number will increase to 8, right? It will change into cesium chloride structure, right? So effect of pressure on ionic solids, effect of pressure and temperature on ionic solids. What is the effect of pressure and temperature? Now high pressure will favor high coordination number. That is, if you apply high pressure onto the structure of sodium chloride, its coordination number will increase. Its normal coordination number is 6. So on applying high pressure, the structure of sodium chloride will change, right? And the coordination number in the resulting structure would be 8, right? So if we have noticed that in cesium chloride the coordination number is 8, right? So when you apply pressure on sodium chloride, right, high pressure, if you apply high pressure on sodium chloride, it will change into cesium chloride, right? This sodium chloride structure will change into cesium chloride structure with coordination number of 8, right? Because high pressure will favor high coordination number, right? So the coordination number initial was 6, so on applying high pressure it will change to 8. That is, sodium chloride structure will change into cesium chloride structure, right? And your high temperature will favor low coordination number, right? High temperature will favor low coordination number, or low temperature will favor high coordination number, right? Just remember this. And high pressure will favor high coordination number, right? So these are some rules that you should remember, right? So I hope all this is clear, right? Just make sure that we know all that we have studied in the structure of sodium chloride, right? And cesium chloride, in cesium chloride, just remember that this is not BCC, but this is simple cubic unit, because we are looking at the location of similar particles which are chloride ions and are located at the corners of the octahedron. And also understand how to calculate the number of particles in a unit cell, right? I hope all this is clear to you. Thanks.